Imagine you're standing outside one of the most power-hungry facilities ever constructed.
Right, yeah.
You're just looking at this sprawling artificial intelligence data center. I mean, rows and rows of these brutalist, windowless buildings, just like stretching toward the horizon.
Oh, and housing tens of thousands of servers.
Exactly. And inside, there's just this relentless, deafening hum. These facilities are, they're pulling gigawatts of electricity from the grid just to train the next generation of massive AI models.
Which is a staggering amount of power.
It really is.
Yeah.
And historically, we look at these structures as this looming threat to a pretty fragile electrical grid, right? Like a colossal, unyielding weight on our energy infrastructure.
Yeah, that's the standard view.
But what if, instead of being the exact thing that fractures the power grid, those massive AI clusters were actually engineered to be the ultimate shock absorbers, keeping it stable?
It's wild, right? Because it completely inverts the physics and, honestly, the economics of large-scale computing. Like, we are conditioned to view data centers as these passive black holes for energy. They pull power, they generate heat, and they offer, zero flexibility to the utility companies feeding them.
Just a one-way street.
Exactly. But the engineering reality we're looking at today completely flips that script. It proves that the flexibility is actually already built into the silicon. It just, it needed the right software to unlock it.
Okay, let's unpack this, because that is our exact mission for today's deep dive. We are unpacking a highly consequential submission to the Open Compute Project, the OCP, for the EMEA region.
A really fascinating paper.
Yeah, it's titled AI Data Centers as Grid-Responsive Flexible Loads. And this is a collaborative engineering demonstration executed by Benthaus and Supermicro.
Right.
If you have any stake at all in the future of AI infrastructure or, energy markets or just grid reliability in general, this research fundamentally rewrites the timeline of what's even possible.
It really does. And the central objective of this deep dive today is to dissect how a vendor-neutral software architecture can take this static, entirely non-interruptible AI infrastructure,
which is how we usually think of it.
Right, and transform it into a highly dynamic, grid-responsive asset. And I think the critical differentiator in this paper, the thing that blew my mind, is the total absence of new hardware.
Wait, none?
None. No proprietary chips, no custom server racks, nothing like that. They achieved millisecond-level grid responsiveness using standard, off-the-shelf, OCP-aligned infrastructure.
That is insane. But before we get into the actual mechanics of how they, physically did it, we have to look at the sheer scale of the collision course we're currently on.
Oh, absolutely. The scale is everything here.
Right. Because the paper explicitly maps out this intersection between modern AI development and modern electrical grid management. On one side, we have AI and HPC high-performance computing data centers, and they're rapidly scaling up to become the most power-dense, concentrated loads on the entire grid.
Yeah, we are seeing a historic phase transition in data center architecture right now.
How so?
Well, for years, a large compute cluster might draw, say, tens of megawatts.
Okay.
And that is significant, sure, but it's manageable within traditional grid planning. But the paper correctly identifies that the industry is accelerating toward aggregate deployments at the gigawatt scale.
A gigawatt. It's hard to even wrap your head around a gigawatt.
It is. A single campus drawing a gigawatt of power is structurally identical to taking a major metropolitan city's entire industrial base and just placing it onto a single node of the transmission grid.
Wow.
And currently, the grid operators are forced to treat these facilities as static, non-interruptible consumers.
Right, so when a utility company looks at a gigawatt data center, they basically just see a massive switch permanently flipped to the on position.
Pretty much.
Like, if the data center negotiates for a gigawatt, it expects a gigawatt 24/7, without any fluctuation whatsoever. It doesn't matter what is happening on the supply side of the grid.
Yeah.
If it's a hot day, if a power plant goes offline, they don't care.
No, they don't. And that's a huge problem because the supply side of the grid is undergoing its own massive, incredibly volatile phase transition.
Right.
The paper notes the accelerating integration of renewable energy, severe transmission congestion, and obviously the increasing frequency of extreme weather events.
Right. The grid is getting more unpredictable.
Very. And grid stability relies entirely on inertia and perfect real-time balance. Like in a traditional grid dominated by coal or nuclear plants, you have these massive physical turbines.
Just literally spinning metal.
Exactly. Giant physical masses spinning at exactly 60 hertz in the US or 50 hertz in Europe.
Okay.
That physical rotating mass provides actual kinetic inertia. So if demand suddenly spikes, the physical momentum of those turbines acts as a buffer.
Oh, I see.
It gives grid operators a few critical seconds to react before the frequency drops to a catastrophic level.
But wait, as we replace those massive physical turbines with, like, solar panels and wind farms, we lose that physical inertia, right? Because solar panels don't spin.
Exactly. They rely on inverters to synthesize that AC frequency, which means the grid is fundamentally losing its physical shock absorbers.
Wow.
When a thick cloud bank rolls over a massive solar array, the megawatt drop-off is practically instantaneous.
Just boom, gone.
Boom, gone. And without that physical inertia to buffer the system, grid operators are getting increasingly desperate for fast-acting, flexible resources.
They need help.
Desperately. They need loads on the grid that can provide rapid curtailment, dynamic load balancing, and active frequency regulation. Basically, they need consumers who can detect a frequency drop and instantaneously pull back their own power consumption to keep the grid perfectly balanced at that 60 hertz.
So if we look at the raw physics of this mismatch, it's a terrifying scenario. I kind of think of it like it's like trying to fill a massive, completely inflexible swimming pool.
Okay,
right?
I like that.
But you're using a garden hose that just randomly changes water pressure every few seconds.
That's just a very accurate, if slightly stressful, way to look at it.
Yeah. You have a grid losing its ability to buffer sudden changes in power while simultaneously attaching the largest, most rigid, highest density power consumers in human history.
It's a recipe for disaster.
But wait, here's my skeptical pushback on this whole thing.
Lay it on me.
How does a grid operator actually expect an AI data center running billion-dollar mission-critical training workloads to just, be flexible?
Right.
If you're in the middle of a massive LLM training run that takes, like, 4 months and costs tens of millions of dollars in compute time, you cannot just let the utility company cut your power because the winds start blowing in West Texas.
You absolutely cannot. And if we connect this to the bigger picture, that tension is exactly why data centers have historically flat out refused to participate in these grid curtailment programs.
I don't blame them.
Right. The operational mindset in enterprise infrastructure is strictly binary.
On or off.
Exactly. A server is either fully powered, processing its tensor operations at maximum clock speed, or it is shut down. And shut down means your workload fails, your network connections drop, and you breach your SLAs with your clients.
Which means you lose millions.
Which is unacceptable. But the bentos and supermicro demonstration shatters that binary framework entirely.
Okay, how?
The proposition here isn't about turning servers off. It is about aggressively, dynamically modulating their power consumption in real time.
Modulating.
Operating in the gray area between 100% utilization and being entirely powered down.
So it's about modulating the power limit rather than actually severing the power supply.
Exactly.
Okay, let's dig right into the architecture of this engineering demonstration. Because translating a distress signal from a grid operator into a physical reduction of power inside a GPU without crashing the software, that has to require an incredibly precise sequence of events.
Precision is the key word here.
The paper outlines a deterministic closed-loop control architecture, and it operates across 4 distinct stages.
Yes. And this 4-stage loop is the exact mechanism that bridges the gap between macro-level grid volatility and micro-level silicon management.
Okay, walk us through stage 1.
So stage 1 is grid dispatch signal ingestion. Basically, the system is designed to receive curtailment or dispatch signals directly from a curtailment service provider, or a CSP.
Okay.
The authors specifically aligned their demonstration with the operational practices of CAISO, that's the California Independent System Operator.
Right, so CAISO monitors the grid, they detect a sudden drop in supply, and they broadcast a digital signal demanding immediate load reduction from participating industrial consumers.
Spot on.
And then the Ventus architecture basically just receives that inbound network payload.
Correct. But, receiving the signal is trivial, right? Acting on it safely is the complex part.
Sure.
Which moves us to stage 2, orchestration and constraint resolution.
Okay.
The external energy orchestration control plane, which was developed by Ventus, intercepts that CAISO signal.
It grabs it.
Right, but it does not just blindly forward a power down command to the server racks. It has to act as a highly sophisticated translation layer. It ingests the macro grid demand and cross-references it against real-time, micro-level hardware telemetry.
So it's performing complex constraint resolution. Yeah. It has to calculate precisely how much power can actually be stripped away from the active servers without violating DCIM data center infrastructure management safety protocols.
Exactly. It is continuously calculating the operational floor.
The floor.
Yeah, it looks at the current thermal states, the active workload utilization, and the minimum voltage requirements of the specific hardware in that moment.
Wow.
The Bento software mathematically resolves the safest, most aggressive power reduction target possible within those strict physical boundaries.
Okay, so once that math is finalized, we hit stage 3, which is real-time GPU power modulation.
The actual physical event.
Right, this is the physical execution.
Yeah.
The orchestration plane pushes those new mathematically constrained power targets down to the physical hardware.
Yeah.
In this pilot, they used supermicro systems loaded with NVIDIA B200 GPUs.
Very high-end hardware.
And they executed this utilizing entirely open standard DCIM power management interfaces.
And this is a crucial distinction that we have to emphasize.
Why is that?
Because they are not hacking the firmware, they aren't inventing a backdoor, they are communicating through standardized out-of-band management protocols.
Like what?
Things like Redfish APIs or IPMI. These are natively supported by the Supermicro baseboard management controllers out of the box.
Wow.
They just send a legitimate standards-compliant command to the GPU saying, hey, your new maximum power draw is now reduced by 40%.
And finally, stage 4, telemetry feedback and acceptance.
Yeah.
The control plane doesn't just fire off the command and walk away hoping for the best, right?
Right, that would be reckless.
It initiates a high-frequency polling loop. It reads the telemetry back from those B200s to verify that the power draw has physically dropped, confirming the silicon is stable at the new voltage limit.
It verifies the physical reality matches the software command.
Exactly. And then it packages that confirmation into an acceptance signal that is transmitted right back to QSO.
So the grid operator receives cryptographic verification that the requested megawatt reduction has been physically realized on the network.
Okay, so to visualize this entire loop, I kind of think about a highly trained orchestra, right?
Oh, go on.
Like the grid operator, QSO, is the composer. They send the sheet music, the raw demand. That's step 1.
I like this.
The Bento's software is the conductor. It intercepts the music, interprets it, and figures out how the instruments can safely play at step 2.
Right.
Then the NVIDIA B200 GPUs are the musicians themselves, physically playing software on command step 3.
And then the sound engineer in the back.
Yes. The sound engineer confirming the audio levels on the monitors is a telemetry feedback verifying everything sounds right. Step 4.
That analogy holds up perfectly when you look at the physics of what is happening inside the B200s. The AI workload is the forward momentum of the song. It doesn't halt, the musicians don't pack up and leave. It just experiences a shift in how much energy it's allowed to consume to keep moving. But to fully appreciate the gravity of this paper, we really have to reiterate the underlying constraint they operated under.
Remind me.
They achieved this incredible flexibility entirely through software-defined orchestration layered over existing OCP-aligned management interfaces.
They didn't have to wait for the next generation of silicon to be fabricated with like special grid compliance modules built into them.
Precisely. The standard out-of-band management interfaces that vendors like Supermicro already implement just for basic data center telemetry possess the inherent capability to enforce dynamic power limits.
It was just sitting there.
The capability was lying dormant the whole time. The missing link was just this deterministic orchestration layer capable of bridging the chaotic high-stakes environment of the energy markets with the fragile, microsecond-sensitive environment of GPU power delivery.
Okay, that brings up a critical engineering hurdle. When you're dealing with grid operators, especially in markets saturated with volatile renewables like wind and solar, the window for action is brutally short, right?
Oh, incredibly short.
When KSO sends out a fast demand response payload, they are typically targeting systems like massive industrial battery arrays. And batteries are chemical. They can inject or absorb power from the grid almost instantaneously.
Yep, they're the gold standard for speed.
So if you are going to pitch an AI data center as a viable alternative to a giant lithium-ion battery array for grid stabilization, Just how fast does this four-stage control loop actually execute?
Well, the paper isolates this exact metric, focusing on ultra-low latency and absolute repeatability. To even participate in these premium frequency regulation and fast response markets, independent system operators usually mandate that the entire loop, from signal ingestion to physical load reduction and telemetry acceptance, must be completed in under 2 seconds.
2 seconds.
That 2-second threshold is the gold standard for grid responsiveness.
Okay, let's look at the actual data from the pilot, because Figure 2 in the paper breaks down the latency across 3 distinct test events, and the numbers are just staggering.
They really are.
In Test 1, they commanded a power limit reduction of 30%. The total round-trip latency across all 4 stages was 19.4 milliseconds.
We need to contextualize that. The grid demands a response in 2,000 milliseconds.
Right.
The bentos and supermicro architecture achieved it in 19.4.
Here's where it gets really interesting. Test 2 pushed the system much closer to the edge, demanding a massive 70% reduction in power.
A huge drop.
The total latency there was 20.7 milliseconds. And Test 3, another massive 70% reduction, executed in 17.3 milliseconds.
It's incredible.
So averaging across the board, the system reacted in 19.13 milliseconds. 2 seconds is a fast reaction for a human. 19 milliseconds is literally a fraction of the blink of an eye.
Yeah, a human blink is roughly 100 to 150 milliseconds. This is happening 5 to 7 times faster than you can blink.
That's absurd.
And the latency breakdown is where the engineering really reveals itself. The dispatch ingestion receiving the payload from the simulated grid provider took roughly 2 milliseconds.
Okay.
Generating and transmitting the acceptance signal back to the grid took about 1.6 milliseconds.
What about the orchestration layer? That complex constraint resolution math, ensuring the thermal limits and voltage floors are respected before issuing the command.
The orchestration overhead was mathematically negligible.
Really?
The bentos control plane processed the logic in 0.00074 to 0.0102 milliseconds.
Wait, 10 microseconds.
10 microseconds.
That implies the control plane is operating more like a compiled, deterministic, real-time operating system rather than like a standard enterprise software application.
Exactly. It bypasses all the traditional jitter you'd expect in a normal network stack.
So if the software and networking take roughly 3.6 milliseconds total, where's the rest of the time going?
The vast majority of that 19.13 milliseconds, specifically between 13.6 and 16.8 milliseconds, is consumed by the physical GPU power modulation itself.
The actual hardware.
This is the unyielding physics of the hardware. When the Supermicro baseboard management controller receives the command and tells the voltage regulators on the NVIDIA B200 to drop the power by 70%, it doesn't just happen in a vacuum.
Right.
Capacitors have to discharge, the voltage regulator modules have to physically step down the voltage, the silicon has to adjust its clock frequencies to remain stable at that new lower voltage.
Oh, wow.
That physical settling time within the electrical components accounts for the 14 millisecond bulk of the latency.
Hold on, let me push back on this.
Mm-hmm.
Because you are talking about slashing the power to one of the most complex pieces of silicon on Earth by 70% in less than 20 milliseconds.
Yes.
If I install a third-party tool on my home workstation and suddenly yank the power limit of my consumer GPU down by 70%, well, it's, say, rendering a 4K video.
Yeah, I know where this is going.
The system immediately blue screens. The voltage drops way faster than the clock speed can adjust, the transistors fail to flip, the registers corrupt, and the OS just panics.
It crashes hard.
Exactly. So how are they executing a 70% drop in 14 milliseconds on a multi-million-dollar B200 cluster without catastrophically bricking the hardware and corrupting the AI model?
It's a great question. The reason your home workstation crashes is that a blunt power cut violates the internal safety margins of the silicon.
Okay.
You are basically starving the chip of voltage while it is still actively attempting to execute instructions at a very high frequency.
Right. It expects power that isn't there.
What this architecture leverages is dynamic voltage and frequency scaling, or DVFS.
DVFS, okay.
And this is managed through deeply integrated hardware control loops. The orchestration layer doesn't just cut the power supply at the wall, it rewrites the power limit registers via the out-of-band management interface.
So it's negotiating with the GPU's internal firmware rather than just starving the power supply units.
Exactly. When the B200 receives that new power limit command, Its internal microcontroller instantaneously executes a perfectly synchronized step-down.
Oh, I see.
It aggressively gates its clock speeds, purposefully slowing down the frequency of the tensor cores, which inherently lowers the voltage requirement.
So it slows down before it starves.
Right. And the Bento's control plane is continuously polling the DCIM telemetry to ensure this step-down perfectly tracks within the vendor-supported safety envelopes.
Wow.
It acts as a deterministic shock absorber, guaranteeing the silicon never steps outside of its physical operating parameters, even during an incredibly violent 70% dynamic load reduction.
And it has to do the exact same thing in reverse, right? Like when the grid emergency is over 15 minutes later, it has to release that limit and let the GPUs ramp back up to 100% utilization without causing a massive power spike that trips the data center's own internal breakers.
That is so important. The recovery phase is arguably just as delicate. If a gigawatt data center instantly pulls back to 100% load, the sudden transient spike in current could literally melt the facility's switchgear.
Yeah.
So the orchestration layer manages the ramp up just as tightly as the ramp down, ensuring a smooth, compliant return to baseline operations.
So we've established the raw speed, 19 milliseconds,
Sure.
and we've unpacked the physics of why the hardware doesn't physically melt or crash.
Yes.
But we have to look at the other side of the equation. The AI itself.
But the business side.
Exactly. Data center economics are entirely dictated by SLAs, service level agreements.
When clients rent a cluster of B200s for a massive training run, they expect absolute operational continuity.
They're paying millions, they expect perfection.
Right. If this system interrupts the workload, even for a fraction of a second, the technology is commercially dead on arrival.
Absolutely. The commercial viability rests entirely on the concept of operational continuity, and the paper makes this unequivocally clear.
Okay.
What's fascinating here is that the dynamic power limit reduction is utilized specifically instead of shutting down nodes or halting workloads.
They never turn off. Never. Let's look closely at the results of those extreme 70% reduction tests. The authors state that thermal and electrical compliance was maintained perfectly, and crucially, they observed 0 system resets and 0 workload interruptions.
The tensor operations just keep calculating.
The workloads do not fail, they just stretch.
They stretch.
Structurally, the AI application running on top of the Linux kernel and the NVIDIA drivers is largely agnostic to the physical power limit of the underlying silicon.
Oh, really?
Yeah. When the orchestration layer slashes the power by 70%, the DVFS systems drop the clock speeds. The GPU is now executing fewer matrix multiplications per second. The memory bandwidth slows.
Okay.
To the AI researcher monitoring their training run on a dashboard, it simply appears that the throughput of the cluster has temporarily decreased. The progress bar just slows down a bit.
So, practically speaking, if a massive cloud bank covers a solar farm in California, say SO sends the distress signal.
Yep.
Within 19 milliseconds, the Bento software throttles the supermicro cluster. The grid completely avoids a catastrophic frequency drop.
Disaster averted.
And the AI model, which was, scheduled to finish training in 45 days, might now finish in 45 days in 2 hours.
Precisely.
It's a completely invisible, frictionless process for the end user, but it preserves the uptime and the SLA for the data center operator.
And this behavior is incredibly robust. The paper emphasizes the repeatability of this dynamic response.
They did it more than once.
Oh, across dozens of test cycles, varying the curtailment percentages and the baseline load of the GPUs, the ramp magnitude and the recovery behavior remained tightly bounded and predictable.
Wow.
This isn't just theoretical modeling. This is empirical proof of a robust, financially viable mechanism for load flexibility that actually protects the core business model of the data center.
Okay, let's zoom out and look at the macro implications of this.
Let's do it.
We have a 19 millisecond response time that preserves workloads and protects hardware. How does this architecture rewire the fundamental relationship between hyperscale tech companies and global energy markets?
Well, it recategorizes AI data centers entirely. They go from being the grid's biggest liability to being its most valuable stabilizing asset.
That's quite elite.
It is, but historically, grid operators manage volatility by keeping natural gas peaker plants on standby, spinning reserve that can inject power when demand spikes, or by aggressively cutting power to massive industrial loads like aluminum smelters.
Right, which takes a while.
Exactly. This demonstration proved that AI infrastructure can actively bid into emergency curtailment markets, fast demand response markets, and even secondary balancing services.
So what does this all mean? The paper explicitly ties these capabilities to the North American Electric Reliability Corporation, or NRRC.
NRC, yes.
NRRC writes the operational guidelines for grid stability, and they require incredibly fast, highly measurable responses for active frequency control.
Extremely strict requirements.
Right. Traditional demand response, like asking a factory to shut down, takes minutes. But this 19-millisecond response time doesn't just meet NERC guidelines for basic load shedding.
Yeah.
It actually qualifies the data center to participate in active frequency regulation.
Which is a much higher value tier of grid stabilization.
It's premium.
And because this relies on standard OCP interfaces, the physics and the protocols are universally applicable.
It's not just a U.S. thing.
Not at all. The paper was submitted for the EMEA Open Compute Project, right? Europe, Middle East, Africa. And the authors actually validated the control loop with additional lab testing in the Netherlands.
Oh, I missed that.
Yeah, the out-of-band management interfaces on a Supermicro server in Amsterdam operate identically to one in Texas. This is a globally portable architecture.
That actually brings up a massive bottleneck in the current AI boom: power permitting.
Oh, the permitting is a nightmare right now.
Right now, tech giants have the capital and they have the chips to build gigawatt-scale campuses. But they are just stuck in a queue because local grid operators are terrified to approve a new 1-gigawatt interconnection.
Of course they are.
The utilities know they don't have the transmission capacity to guarantee that level of power 24/7. But if a data center operator walks into that permitting meeting and proves they are a flexible load, that they can instantaneously throttle their demand by 70% the exact millisecond the grid experiences stress, how does that change the math for getting these massive facilities built?
It fundamentally de-risks the interconnection agreement for the utility company. The data center transforms from a parasite into a symbiotic partner.
That's a great way to put it.
Future AI clusters can be architected to operate dynamically within whatever limited megawatt capacity the grid can safely provide at any given second.
So they just use what's available.
Exactly. They can absorb excess renewable generation when the sun is shining and power is super cheap and instantly yield that capacity back to the grid during, say, peak evening demand when everyone gets home and turns on their AC.
Wow.
It is the only mathematically viable way to reconcile the exponential growth of computational demand with the hard physical constraints of our existing power grids.
And the timeline for deployment. This might be the most disruptive detail in the entire paper.
Yeah, the timeline is shocking.
The authors state that because this solution relies entirely on existing, vendor-neutral software orchestration layered over hardware that is literally already sitting in racks today.
Right.
Because they don't have to invent a new chip or, wait for a new OCP standard to be ratified by committee, they estimate this capability is deployable in production environments within a 6 to 12-month timeframe.
I mean, in the context of energy infrastructure, where planning a new high-voltage transmission line takes a decade, and in enterprise IT, where hardware refresh cycles take 3 to 5 years, a 6 to 12-month deployment horizon is basically instantaneous.
It's tomorrow.
It means the capability to stabilize the grid using AI workloads is available today. It really just requires the deployment of the orchestration software.
Okay, let's pull all of this together for everyone listening.
Sounds good.
We began by looking at the existential threat of gigawatt-scale AI data centers, just totally collapsing our volatile, renewable, heavy power grids.
The standard narrative.
Right. But by dissecting this Bentos and Supermicro OCP submission, we've uncovered a massive paradigm shift. By leveraging software-defined orchestration and standard DCIM interfaces, we can force multi-million-dollar AI clusters to react to grid instability in 19 milliseconds.
19.13 to be exact.
Right. We can dynamically scale their power draw up and down like a transmission shifting gears, absorbing grid volatility without ever dropping a single compute workload or violating a hardware safety envelope. The biggest threat to the grid is actually its greatest potential savior.
It really is. And this raises an important question, something for everyone to really chew on.
Oh.
Yeah, as we watch this technology transition from an engineering demonstration into actual production deployments over the next year, it forces us to consider the next logical evolution of this architecture.
Where does it go from here?
Well, today, human engineers have written a deterministic control plane that allows the hardware to respond to external grid signals, right?
Right.
But as the AI models training inside those data centers become increasingly autonomous and capable of optimizing complex systems, how long until the AI natively negotiates its own power consumption?
Oh, wow.
Imagine an AI that inherently understands its own training deadlines, monitors the millisecond by millisecond wholesale price of wind and solar energy on the open market, and autonomously throttles its own processing speed to optimize for both its compute budget and the real-time health of the grid it relies on.
That is mind-bending.
The architecture we explored today proves the grid can be software-defined. The question now is whether the future of the power grid will ultimately be AI negotiated.
Well, next time you see the news about massive data centers draining the power grid, just remember the 19 milliseconds we talked about today. The infrastructure isn't just consuming the grid, it might actually be the only thing fast enough to keep it all perfectly balanced.